Going to space is incredibly hard. Modern rockets are basically giant bombs controlled by computers, and 90% of their weight is just fuel. But what if we didn't need rockets? What if you could just press a button, step inside, and ride all the way into the cosmos? Welcome to the space elevator. This is the ultimate megastructure that could make space travel as cheap and easy as a plane flight. To build this mind-bending machine, we need three main parts. First, the base station, a massive floating platform anchored in the ocean near the equator. Second, the counterweight, placed way out in space. This could be a captured asteroid or a massive space station to keep the entire structure pulled tight. And finally, the tether, a ribbon-like cable. It connects the Earth to the counterweight, stretching an unbelievable 36,000 kilometers. How does it stay up without collapsing? Simple physics. Imagine spinning a rock on a string. The faster you spin, the more the string pulls outward. Earth does the exact same thing. As our planet rotates, centrifugal force flings the counterweight outward, pulling the cable taut against Earth's gravity. But here is the ultimate engineering nightmare. The tension on this cable would be so extreme that almost any known material would instantly snap under its own weight. If we used steel, the cable would snap before it even reached a fraction of the way up. We need something 100 times stronger than steel. Enter carbon nanotubes and graphene. These microscopic structures are exactly what engineers have been dreaming of. They are incredibly lightweight, flexible, and have the highest tensile strength of any material discovered by humanity. They are the key to building the tether. With the cable built, we need the climber. This isn't your standard elevator. It would use magnetic levitation, shooting up the ribbon without touching it.
Imagine the journey. You step inside, and the climber accelerates to hundreds of miles per hour. Within minutes, you blast through the clouds.
The bright blue sky fades into a deep, endless black. You cross the edge of space without a single explosion or G-force crushing your chest. Looking down, you see the brilliant curvature of the Earth. A smooth, silent, and entirely safe ride into orbit. But why build this? Economics. Right now, launching a rocket costs around $10,000 for a single kilogram of cargo. The space elevator would slash that price down to just a few $100s. Space would no longer be just for billionaires. It would be open to everyone.
With Part 1 complete, the structure is up and operational. We can now launch satellites, move massive cargo, and send passengers into orbit daily for a fraction of the cost.
Furthermore, the elevator allows us to bring up heavy modules. Instead of launching tiny pieces, we can assemble massive space stations, space hotels, and research hubs. It also revolutionizes deep space missions. Since climbers move material into GEO cheaply, we can build and fuel in orbit, ready to explore Mars, Jupiter, or beyond. But we must address the remaining risks. In low Earth orbit, space debris and defunct satellites travel at thousands of miles per hour. A direct hit could destroy a climber or sever the tether. Mitigation strategies are complex. We need advanced debris tracking, specialized laser brooms to clear orbits, and tethers that are either self-healing. Then there is Earth itself. Hurricanes, tsunamis, and powerful ocean currents at the base put intense stress on the entire system.
And lightning! A 36,000-kilometer conductor stretching into space is a giant lightning rod. The CNT tether must be designed to safely ground high-voltage strikes. Beyond the atmosphere, physical radiation from the sun and the Van Allen belts is a severe danger. Climbers must have robust shielding to protect passengers during the week-long ascent. We must also secure the structure. The elevator is vulnerable to physical attacks. Base stations must dedicated defense zones, and tethers require constant autonomous drone surveillance. Building it also requires unprecedented international political stability. By a single country or corporation, it demands global cooperation. Overcoming these challenges is tough, but the payoff is infinite. The elevator unlocks new technologies, like orbital solar power stations that beam clean energy down the cable to power Earth. It makes asteroid mining economically viable. We can capture asteroids, extract rare minerals in orbit,
and bring them down cheaply to solve resource scarcity on Earth. Most importantly, the space elevator is our first true stepping stone. It opens up the entire solar system for exploration, construction, and, ultimately, colonization. We would cease to be ground-bound observers and become active participants in the cosmos. Access to space wouldn't be a privilege, it would be a right. Interestingly, a lunar space elevator is actually easier to build than an Earth elevator. With much lower gravity and no atmosphere, current materials might actually work there today. Building an elevator to space is the single greatest engineering dream of our time. It is terrifyingly complex, but it is achievable. Are we ready to stop dreaming and start building?
Our universe is full of impossible questions. Subscribe now to keep exploring the ultimate limits of physics and engineering.